So next section is shortest path algorithms. So every edge is associated a weight or a non-negative real number which we'll call as weight to that edge. Such a number is associated with each edge, then you will call the graph is a weighted graph. Okay, so edge having a weight associated with it, numerical value associated with it, you will call it a weighted edge. And all the edges of a graph are weighted edges, then you will call the graph is a weighted graph. So this weight or the number you are associating, it may represent the distance, time, cost, etc., depending on the situation what you are considering as vertices. Okay, maybe that the number is denoting distance between two places, where places are denoted by vertices, right? So, or maybe the time taken for for traveling from one location to another location, or the cost incurred, etc. Okay, so what do you mean by then shortest path? In a weighted graph, a shortest path between two vertices means the path you can find between those two vertices which has the sum of weights of the edges that you are having in the path. It is shortest. So the length of a path means, for a weighted graph also, the length of the path means sum of the edge weights you are having in the sum of the edge weights of the edges that are present in the path, right? So whatever path you are having, find all its edges and edge weights, sum these values, that is the length of the or weight of the path, you can say. Okay, so a path having the least weight for a pair of vertices from one vertex to other, you can find if it's a connected graph, you can find several paths. Out of these paths, what is the path which has the least weight? That is called the shortest path between those two vertices. If it is an unweighted graph, in that case all the edges you can consider having the weight as 1, right, which represent the edge. How many means what is that edge only, right? So one weight you can associate if it's a unweighted graph. So basically the shortest path between a pair of vertices in an unweighted graph becomes the path with least number of edges. So in a weighted graph that need not be the case. The weight, depending on the weight, you can have a shortest path which contains more edges than another path, but the numerical value you associated, it is smaller, that its sum is becoming smaller, right? So in a weighted graph, the shortest path means the path between that vertices which has least weight. What do you mean by weight of a path? It is the sum of edge weights of the edges that you are using in the path. Okay, so if it is a unweighted graph, the shortest path basically means the path which contains least edges. In a weighted graph, it is not the case. So we have an algorithm called Dijkstra's algorithm to find such a shortest path between a pair of vertices. It's an iterative procedure. So this, whatever is written, that in the with an example I will explain. So you have this particular graph. It's a weighted graph. There are this many vertices, so 6 vertices are there and these edges are there, and these edges are now having numbers associated with it. These are not labels, these are the weights, 2, 5, 2, etc. These are the weights, right? So now you want to find what is the shortest path from, say, A to F. So A to F, AF shortest path you want among the AF paths which has the shortest length or shortest weight, right? What is the shortest path from A to F? This is what we are interested in. So applying the Dijkstra's algorithm, we can find it. So this algorithm is an iterative procedure. So we'll start at the iteration 0, where we'll give these details of the what are the vertices. So we'll be iteratively removing the vertices also. We'll be labeling the vertices in each iteration, and we'll remove one vertex in each iteration, from one iteration to the other. The next iteration, once you go, you will remove one vertex. So what is the idea? So you have in the 0th iteration, we will start with the initial vertex. So in the A to F paths, you have several A to F paths. I can take this path, this is one path, this is another path, this is another path, this is another path. So there are several paths from A to F, among which what is the least weighted one. Using the algorithm you have to find. Manually you can check the different paths and find it. If it's not such a lengthy graph, so you can do this, but how to apply the algorithm, that's what. So you are in the initial iteration, zeroth iteration, our vertex set will be all the vertices itself. So from which vertex you are starting the path, A to F paths only you are interested in. So your initial vertex is A, final vertex is F, right? So the initial vertex in the zeroth iteration, you will give a label to the initial vertex as 0, the number 0, and all the remaining vertices you will give the label as infinity. Okay, so right now you have only the vertex is there, no other edges are there. So from the vertex A to itself you can reach, the initial vertex A to itself you can reach, right? So the labeling you are giving, you are denoting by L of this vertex at V0. So it is, so yeah, labels for the vertex at V0 you are having, right, which is basically in the initial stage it is all the vertices in the graph itself, right? So now the initial vertex of the path you are trying to find, it will be given in the zeroth iteration 0 as the label, remaining all vertices as infinity. Now in any iteration which label is the smallest, that particular label you will make a bracket bracket to it, and the corresponding vertex, once you go to the next iteration, you will remove from the vertex set and you will denote that by putting a star on it. So in the zeroth iteration, A receives label 0, all the remaining vertices receives infinity as a label, because A is the starting vertex for the path you require. Okay, so the label for A it is 0, so A is removed in the next iteration and there is no label also for it. Okay, so you'll star that vertex A also. So your V1 now contains B, C, D, E, F only, right? The removed vertex from the previous stage, it is A. Now with the removed vertex from the previous stage to this stage, which vertex is removed, you will find for that vertex to the remaining vertices what is the edge weight. If there is an edge from that vertex to the remaining vertices, what is the edge weight, you will find that edge weight plus, if there is an edge, then only that edge weight will be there, right? So that, otherwise it will be infinity itself, right? So that edge weight plus the label of the removed vertex to this stage. Once you come to this stage, what is the removed vertex? The label of that vertex plus weight of the removed vertex to the vertex you are considering in this stage, right? Each of the vertex you are considering in this stage, what is the edge weight? So that sum will be the new label, new possible label for the remaining vertex. But this label you will replace only if it is smaller than the previous label you are having. So previously you are having B, C, D, E, F are all having infinity as a label. So any other number you get as a label here, you will be having, you can replace it with this new label. Okay, so in the iteration 1 we are having the set V1, vertex set V1 is not having A, because A has been A is the permanent vertex you have fixed in the last stage. So you are now not considering A, so you are removing that vertex basically, from that V0 to form V1, and now you are finding this removed vertex, what label it gives to the remaining vertices, and if that label is less than the previous label, you will replace the label for these vertices, and then you will again repeat the process. Find the minimum value, bracket it, remove the vertex once you go to the second stage, right, and again do the same process. Find for this removed vertex what is the new label that you will be applying this procedure for each of the vertex, and find the minimum means replace it once if it is less than the previous label you are having for that vertex, and find the minimum and bracket it, remove it, so on, right? So in the stage 1, from from 0 to 1, if you go in iteration, you are removing it is start, right? It's the start, it's the vertex that is given star. Now you'll find the label for B by checking what is the edge weight of A to B. It is 2 plus the previous label or the label of the removed vertex A, which is 0. The permanent label you gave for A, it is 0, so that plus the edge weight of AB, so that will be the possible new label for B if that value is less than the previous label B has. Previously it was infinity. Now you are having 0 plus 2. 0 is the label of A, removed vertex A, plus weight of A and B. A is the removed vertex. So this is nothing but 0 plus 2, which is 2, which is less than infinity. Therefore you can replace the label of B as 2 in the first iteration. Similarly for C, it was infinity before. Now it will be A star its label plus weight of AC, which is 3. So 0 plus 3 will be the new label. Now for D, A is not adjacent to D, therefore we will be getting infinity itself as the label out of this procedure, and previous label was also infinity, so D will be infinity itself. A is not adjacent to D, E or F, therefore their labels also don't change, it will be infinity itself. Okay, so the only changed labels are this. Now among the values now you are having, A doesn't receive any label now, A has already a permanent label. Now for the remaining vertices, you gave the new labels, and among that 2 is the smallest, we will bracket it, the corresponding vertex we will remove in the second iteration, we will star it, and there is no label for B also. Now A and B are without labels. Now for this removed vertex B, we will find the possible new labels for these vertices. Okay, B, its label is 2, so that plus B to C, if there is an edge, that you have to add, but B to C you don't have an edge, which means this labeling method L of B plus weight of BC will give you infinity only, and that is not smaller than the previous label of C, which is 3. Therefore 3 itself you will repeat here. You are not going to change the label from the previous stage. Okay, now for D, B is adjacent to D, its weight is 5, B's permanent label was 2, so 2 plus 5, 7 is the value you get in this stage. The label, possible label for D, it is 7. Previous stage it was infinity, so this label is less, so you will replace that infinity label with 7. Okay, now for E, B is adjacent to E also, its edge weight is 2, B's permanent label was 2, so 2 plus 2, 4. That 4 is the new label possible, and it is smaller than the previous label infinity, therefore you will replace E's label also. B is not adjacent to F, so whatever was the previous label of F, that itself will be repeated. This is the second iteration. Okay, now you bracket 3 because that is the smallest, remove the vertex C. Once you go to the third iteration, your V3, now it will be A, B, C, all are starred, C is the newly starred vertex. Now we will find the labels for the remaining vertices, right? So C to D you don't have an edge, so whatever was the previous label, that itself stays, so 7 is the label for D. C to E you have an edge, which is edge weight 5, so 5 plus C, its permanent label was 3, so 3 plus 5, 8, so that 8 is not less than the previous label, therefore you won't replace the label here, you will keep the previous label itself, which is 4. Right, now C is the removed vertex from stage 3. This is stage 2 to stage 3, or iteration 2 to iteration 3. C is the removed vertex. Now for that you have to find the new label possible for F also. C to F there is no edge, therefore the previous label won't change, it will be infinity itself. Previous label it is infinity, that itself we repeated here. Now among this 4 is the smallest, bracket it, remove this edge E to the next stage. For fourth iteration E will be removed, so A, B, C. Now E is also start, its label is now empty, or its label is removed. It got the permanent label in the previous stage. Now E, it is adjacent to D and F, so it can change this, remove this permanent vertex E star now can change the labels of the other vertices D and F. E is adjacent to D, its edge weight is 1. Okay, so 1 plus the permanent label of E, it is 4, so 4 plus 1, 5. 5 is the label you get in the fourth iteration for D. Previous label was 7, so you'll replace the smallest one, which is 5. Now for F, it is for the deleted or removed permanent label vertex E. What is the edge weight? It is 4. The permanent label of E also is 4, so 4 plus 4, you will be getting 8 as the, by following this procedure you will be getting 8 as the new label for F. Previously it was infinity, so 8 is the smallest, you will replace with 8. Okay, so now in the fourth iteration, what is the smallest value? 5. So the corresponding vertex D, that label will be bracketed, D will be given that permanent label, and it will be removed from the vertex set. In the fifth iteration V5, the vertex set will be having all these as permanent labeled, and all these so including D is permanent labeled. If it is not permanent labeled now, only remaining vertex is F. Until you reach F in this iteration, you have to continue. So now we are, until you give the permanent label to F, you have to continue. Now we are going to give the permanent label to F. So this is the removed vertex from the, or the permanent label vertex from the previous stage. Its label was 5. D is adjacent to F, so 5 plus the edge weight of DF, it is 2. 5 plus 2, 7 is the value label that you can give in this stage if it is smaller than the previous label. So the previous label is 8, now you got 7, so you can replace it, and this is the smallest among the numbers you are having here, only that number is there, so you'll bracket it, that will be permanent vertex also. So once that terminal vertex of the required path is given the permanent label, your algorithm stops. Now what you do is you trace back the, to get the path, shortest path, you trace back the vertices which received the permanent label in the previous stages. Okay, so F received the permanent label because of this value 7 is there. That value 7 came in the previous stage, it was 8, now it is 7. So this 7 came because of the vertex that became permanent in the last stage, it is D. So D should be the vertex that is preceding your F. Okay, now D received the permanent label 5 in this stage only, right? So previously it was 7. So which vertex was permanently labeled in the third stage, that gave 5 as the permanent label for D. So which was that? It was C, right? So C was the, sorry, it was E. E was the vertex, E was permanented, so E was the vertex that gave D the permanent label. So the preceding vertex to D, it will be E. Now E has the label, permanent label as 4. In the previous stage also it was 4. So the vertex that was removed in, or that was permanented in second stage, that is not giving the label 4 to E, the permanent label 4 to E. It was given in a previous stage, right? It is not from this stage, it is from this stage, right? In the first stage it was infinity, second and third stages it was 4, but in the fourth stage only it is permanent. So which vertex gave permanent label 4 to E? It is not from the second iteration, it is from the first iteration. Whichever permanent vertex you obtained in the first iteration, that only changed infinity to 4, right? And that 4 stayed. So that is the corresponding vertex preceding E. Preceding E, it won't be the permanent vertex C in the second stage, because C didn't give 4 as the label for E. So it was given by B. So preceding E, you'll be having B, right? You'll be having B. Now preceding B, which its permanent label is 2, and this label was in the previous stage it was another label. So this label was obtained by the permanent vertex that is there in the previous stage, 0th stage, which is A. So preceding B, you'll be having A. So this will be the corresponding shortest path. So that is the algorithm. If you check the sum of edge weights of this particular path, you are having, it is 2 plus 2, 4, 4 plus 1, 5, 5 plus 2, 7. 7 is the shortest path weight you'll be getting. So you can check any other path you take, its weight will be more. So if I take, say, this one, 3, 5, 8, now itself it is 8. So the shortest path contains or cost or the edge weight is 7, right? So any other path you take, it will be having more edge weight among the AF paths. Okay, so 2, 2, 1, 2. This is the path we said, right? So which is the shortest path. Or if you take, say, 2, 5, 1, it is going to be 8. 2, 5, 2, it is going to be 9. 2, 5, 1, 4, it is going to be 10. So every other path will be having bigger cost. Okay, so this is the Dijkstra algorithm, iterative procedure. Okay, the same thing is here. So consider another graph. For this particular graph, here having A, B, C, D, E, F, G, H are the vertices. 0th iteration contains all the vertices. You require, say, A H path, A to H path. What is the minimum cost or shortest path you can have? Shortest path you can have. Once you find the shortest path, you find the minimum cost also. So in the 0th iteration, you will be giving the initial vertex of the path, AH paths. Among that, the shortest one you have to find. So A, you will make permanent vertex in the 0th stage, right? So the label will be 0, remaining all will be infinity. So A will be start in the first iteration. Now A2, so 0, the permanent label plus A2, each of these vertex, what is the weight you are having, that will be the possible new labels. So AB it is 2, so 2 plus the label of A, which is 2. So that will be the label for B now, because it is less than the previous label of B. So A to C there is no edge, so it will be infinity itself. A to F it is there, A to G, A to H, it is, there is no edge, therefore A to C till, so C it will be infinity itself. A to G it is not there, so G it is infinity itself. A to D it is not there, so D it's infinity itself. So A is not adjacent to these vertices, means that weight is not there, weight is infinity. So that your label through this method, label of A plus weight of the edge between A and that vertex, if you take, it is going to be infinity itself. There is no edge, means, right? So that it doesn't change. Okay, and so the previous label itself stays. That's what happens. Okay, so A to D, A to C, A to E, A to G, A to H, there are no edges. So for that each of that edge, the label won't change, the same edge label you will give. But for B and F, with which A is adjacent, their labels can change. So here the label of B changed to 2, so 0, the permanent label of A plus 2, right? So that is what you are having. 2 is the new label of B. Now 0 plus 1 will be the new label of F. So among these, so all the remaining will be having infinity as a label. Among this, 1 is the smallest, bracket it, remove it in the second iteration, it became F star now. So A star is removed in the first stage, or it is permanent in the first stage. F star is permanent in the second stage, right? So this is the, so we are not now taking this route, we are taking this route. F is permanented. What is the What is the weight of it? So permanent weight of it, it is 1, so this is 1. Now with F, which vertices, remaining vertices are adjacent. F is adjacent to G, it is adjacent to D. These are the only two adjacencies, so D and G only can change, remaining all will have the same value as before. So infinity here, D can change, G can change, so all others remains infinity. What about D and G? For D it will be the permanent label of F plus the weight here, so it is 1 plus 3 4, and for G it is 1 plus 6 7. Among that 4 is the so there is B also. B, its label didn't change. B already got the label as 2. It was not permanented in the previous stage, so B now has the label as 2. Okay, so you will be having the permanent label 2 given to B. Okay, so B will be bracketed, the weight will be bracketed, and it will be removed in the next stage because that is the smallest here. Okay, so that is the smallest here. So now B is with weight 2, edge weight 2. Okay, so that is bracketed in this stage. Now what are the edge weights to the remaining vertices? B to C, it is 2, so 2 plus 2, this 2 plus the permanent label 2, that is 4. That 4 is less than the previous label infinity, so that you can replace. Now B to E, it is 4 plus 2 6, the previous label is infinity, so you can replace that also. B to D, it is 2 plus 2 4, previous label of D it is 4, now also it is 4, right? So that also we change, we can give for there itself, for itself there. So B to, yes, C, this we gave, D we gave, E we gave. Now B is not adjacent to any of the remaining vertices, so its label stays as before, right? So G, it will be 7, it is 7 before. G, it is 7, so it should be 7 here, and H, it is infinity before, it is infinity itself here. So here the smallest one, you can either choose C or D, whichever one you choose, that will give you the same, means the both of them can give you shortest path. So C, if I am bracketing, okay, one of them I am bracketing, that vertex I am removing. Now we have to reach up to H. Okay, H, once it is permanented, we can stop. We don't have to give permanent label for every vertex. So C, it is permanented now. So okay, now what you'll do, you'll find C to E, B is already removed, C to E and H only you have edges, so E and H only their labels will be modified, can be modified. So G already has 7, right? So now E, what about E? C to E, C, its label is 4, so 4 plus to E, it is 3, so the new label is 7. C to H, it is 4 plus 1 5, so among this 5 is the smallest. It is bracketed, and H is the permanent vertex you are getting. Once you get H as the permanent vertex, you can stop, because we are checking for shortest path from E to H. Now you trace back. H will be the vertex, the final vertex. What will be the previous vertex? This 5 came from C, so C should be the preceding vertex. Now 4 as the label, it came from this stage. So what is the permanent vertex there? It is this one, right? B is the permanent vertex, so it will be B before C, and B got the permanent label 2 from this, not from this. It was already 2 here, so it's not from F, it is from A itself. So before B you'll be having A. So what is that path? A to B to C to H. This is the path. So 2 plus 2 plus 1, 5 is the total cost, right? The length or total cost, it is 5. So that is the shortest path we will be having.